Okay. So Stacey Smith, the question mark is part of her name, is a professor of disease modeling at the University of Ottawa. Using mathematics, she studies infectious diseases such as HIV, malaria, human papillomavirus, COVID-19, neglected tropical diseases, and zombies. She has published more than 20 books on academia and pop culture, is the author of over 100 academic publications, is a winner of a Guinness World Record for her work on modeling zombie invasion, was the winner of the 2015 Mathematics Ambassador Award given by Canada's Partners in Research Association, and won the 2018 Society of Mathematical Biology Distinguished Service Award for exceptional contribution to the field of mathematical biology and its advancement outside of research. And so it's my honor to be able to introduce this afternoon's plenary speaker, Stacey Smith. So.
Right. Yes, thank you very much for having me. And I saw in the chat the word zombies question mark, and it's like, yes, absolutely zombies. Yeah, so if you Google mathematical modeling and zombies, you'll find me there. All right, so I'm not going to talk about zombies though. I'm going to talk about COVID-19 today. So let me just share screen. All right, you can see my screen.
We're good.
Good. Okay. All right. So I'm going to actually kind of do this in two parts. And the first part, I'm going to talk about basically what happened when COVID-19 first hit here in Ottawa. So I'm at the University of Ottawa in Canada. Right now we're full of snow, but apparently so is everywhere else in the continent. So it's not that unusual right now. Basically on March 12th, the university got in touch and they said, we have no models and we need to know what on earth to do about this COVID thing. Right. So this is basically the first bit is a snapshot in time of kind of where we were then, because I want to illustrate kind of how models can be useful. Right. So I'm going to develop a mathematical model and run various scenarios based on what we knew at the time, talk about decisions that were made as a result of these models and various developments since. But I'm also going to talk in the second part more generally about how we know mathematical models are reliable, particularly in pandemics. All right, so now COVID-19, yes, an obscure disease you might have heard of. This is, usually I introduce all the diseases I talk about. This one I probably don't need to introduce too much because we know a lot about it now. All right, so it's a respiratory disease with flu-like symptoms. It's the causative agent of a potentially fatal disease with significant public health concerns that originated in late 2019 in Wuhan, China. All right, so I think we all know about this one. Common symptoms include fever, cough, and fatigue. Other symptoms include sputum production, headache, hemoptysis, diarrhea, dyspnea, and lymphopenia. So there are some, it ranges from, mild to wild, I guess. Death can occur between 6 and 41 days after the onset of symptoms. The median is 14 days. But of course, it depends on the age and the immune status, right? For people under 70, there's more time. And so that median is 20 days. And so just a brief timeline. So on January 22nd, there were 425 laboratory confirmed cases in Wuhan. The initial estimate for R0, for those who don't know, R0 is the reproduction number. Well, I usually introduce that as well, but I think these days many, many people know about this. This is the average number of secondary infections. So this is if I'm infected, how many infections will I cause in a wholly susceptible population by the time I'm done? And by the time I'm done could be by the time I'm dead, or by the time I've recovered, or potentially moved away, or whatever. Right? It's basically just how much damage will I incur. Right? The doubling time was 7.4 days. By February 16th, so a few weeks later, there were 51,000 cases. By March 3rd, there were 90,000 cases worldwide. On March 11th, there was more than 118,000 cases, and it was declared a pandemic by the World Health Organization. So this was taking off at a very, very fast rate, as probably most of us remember. And on March 12th, the University of Ottawa, where I'm at, requested an informal modeling study. Basically, it was desperate emails by the upper administration. And they emailed a couple of us, and it just happened to be on that day, the others were busy and I was free. And I was like, oh, I'm not doing anything today. I'm just at home. Turned out to be very, very much my future. So they were asking what combinations of transmission rates and serial intervals make for the best case and what makes for the worst case. Right. So not knowing a whole lot about what was going on, can we basically run best and worst case scenarios so we get some bounds of what might happen? And then what's the consequence for outbreak size and potential mortality for waiting until case number 1 physically appears on campus versus being proactive? right? So then we're basically saying like, well, it looks like this is coming and it's coming everywhere. So if we see a case on campus, how long do we have and until the first death? And also how likely is the epidemic, going to take off, and how big will it be, right? So I basically did this all in one afternoon and evening. So it was a very fast study, and we had to go pretty quick. The model consists of 6 compartments, right? There are susceptibles, exposed, otherwise known as latent individuals, so they're latently infected individuals. There are individuals who are symptomatic and who can infect. There are asymptomatic individuals who can also infect, and there are recovered individuals. There are also dead individuals. So we keep track of the death because we'd like to know when will death occur and how many people might be dead, but the dead are not an active player in this. Some diseases, of course, the dead do matter, like they matter in zombies, of course, because the dead get up and walk around. But in, for example, Ebola, the dead can still infect you, but that's not the case here. All right, so we're going to define symptomatic individuals as those who both have symptoms and are capable of transmitting the virus. And it's this transmission, I think, that's really key, right? It's kind of a verb, right? It's like, can you actually do something to me? Right? I don't care if you're infected or not. I kind of don't even care if you have symptoms or not. I care, are you going to infect me? Right? But of course, there are people with symptoms who will infect, and then there are people without symptoms who will infect. Presumably people who are asymptomatic infect at a lower rate, although of course we don't know for sure. We didn't know for sure then. And these individuals may also recover faster because essentially they just have less virus. Right? So if you have a lower viral load, it's less bad for you, and also your body fights it off quicker. So exposed individuals are infected but not infectious. Right? So this is effectively a delay because you move into the exposed class and stay there for a while before you become infectious. But once you're in there, you're going to become infectious. Right. Death here is only due to the disease because we're modeling a short time scale. So I'm concerned about how many people will die of this disease and when. I'm not so concerned about will somebody have a heart attack and kill over along the way? Will they die of cancer? Will there be a car accident? Now, of course, all these things are happening and they might have an effect if I'm considering a long time scale. But for a short time scale, I'm only concerned about the disease. Likewise, I'm not replacing the susceptibles, so I'm not really incorporating new babies being born or people coming to campus and so on, because it's really, I want to see what's happening in the short term. But again, if I expand my scale, I might want to think about these numbers. All right, so here's a sketch of the model. All right, and so there are susceptible individuals, exposed individuals, infected with symptoms. There are asymptomatic individuals who are also infectious but without symptoms. There are dead individuals and there are recovered individuals. So those are the variables in my model, and then everything else is a parameter. All right, so remember that variables are things that change, so therefore they have derivatives when I build my differential equations, which I'll do on the next page. And parameters are constants I may not know, but they are constants, so they don't have derivatives. So it's quite easy to distinguish the two. So I have a baseline transmission rate, beta. So that's basically for an infectious person with symptoms, what rate will they transmit at? Right, and so that includes a whole bunch of things, right? It sort of says, what's the probability I'm in the same place at the same time as someone else? What's the chance that transmission will actually occur between two people, and so forth. So it also depends on the number of contacts that we have. And then I may modify that for asymptomatic individuals. So asymptomatic individuals may transmit at a lower rate, although in theory that ETA could be higher, potentially. It's probably not in this case, but it's, of course, the great thing about math is you can run lots of scenarios to see. Some fraction are asymptomatic, right? So 1 minus p go to the symptomatic class and p of them go to the asymptomatic class, but they do this, at rate kappa, right? And so, well, I'm going to say kappa is kind of the rate of developing symptoms. What I really mean is kappa is the rate of leaving the E class. So you leave E and then p determines whether you split into the I or the A. So then there's a leaving rate from the I class. And again, you could leave either to die or to be recovered, and that will be determined by the F, which is the fraction of people who recover, right? So some fraction F recover, some fraction do not. So we assume that either you recover or you die when you leave the I class. You can, of course, stay in the I class forever. That's actually built into the model, but of course, that's a very small number of people who do. And the last parameter here is the amplification factor for recovery of asymptomatic individuals who may recover faster. Now, of course, they may recover slower too. In practice, they're going to recover faster, but we can obviously vary this parameter as needed. Because the great thing is we can play around, right? So we've got our model, and like all models, it's not perfect. This does not 100% describe reality, and there are many tweaks that we could make, indeed should make, and certainly, anyone is welcome to tweak any models and make better models. But the idea is to try and get some insights, right? So we're not trying to build a perfect representation of reality. We're trying to understand what might be going on and see if the model can help us along. All right, so here are the differential equations. So it's exactly the same as the previous page. In fact, every term is in here, but of course we want to write it in differential equation form because then we can actually manipulate it. All right, so the things with primes on them are variables, which are being differentiated with respect to time, and then every other letter that I don't know is a parameter that I can play with. So I can either set it to be an unknown constant and see what happens, or I can use data that I found. And what I'm going to do is basically plug in the data that we did know at the time, and then figure out some stuff about data we might not know and potential ranges. Okay, so here's what we knew on March 12th. All right, we knew that 17% of the population was asymptomatic. The low risk death rate was 0.2%. And because we're looking at a campus population, most individuals on campus are under 70. And so that's not the only factor, of course. There are people who might be immune compromised. So probably some individuals are high risk, but we can maybe assume that the vast majority are low risk. Right, because it tends to be a very young population on campus. I mean, the exception of the professors, of course, that we are not quite as young, but we're a relatively small group. Incubation rate is 3 days, although there's a wide range there, and takes 20 days, as we saw earlier, from onset of symptoms to death in this age group. And the reproduction number by this point had been revised to 2.35, although again, a wide range. And there were 42,000 people on campus, although of course, not every person is on campus at any given time. Now this is, of course, back in March when people were actually going out of their houses and doing stuff, and there were lots of people on campus. So we wanted to make some predictions based on what would happen if we did change nothing, but then also we can see what happens if we do change something. Okay, so some caveats here is that data is often scarce or unreliable in the early stages of a fast-moving pandemic. Right, so these were the most accurate numbers that were available at the time. And as I said, not every individual is on campus at any given moment, so N is likely an overestimate. There's also significant heterogeneity in the susceptible population. Some people may be more susceptible than others for various, immune-related reasons, but also age-related reasons. So, again, we're trying to get some ideas, and then we can, of course, zoom in if we want to examine things in more detail. So if I really care about the few people who might be immune compromised, I could, of course, build that as a separate class and make a revised model. So it's certainly quite possible to make many models for the same situation. All right, so let's do some analysis. So the easy analysis is let's find the disease-free equilibrium. So this has two properties. One is it's an equilibrium, so that means all the derivatives will be 0. The other is it's disease-free, so that means we can set I equals 0 and then see what happens. And it turns out, well, if I is 0, that in the equations implies that E must be 0, and also A, and also R, and also D. So that means that the susceptible population is, as you would expect, everybody. Right? So N here is the total campus population. We set initial conditions as requested in that email. They said, well, what if there is a single case on campus? So I'm going to say a single, infectious person with symptoms. Of course, they might be infectious without symptoms. I wouldn't know that, but I was assumed that they were noticed. And so there was a single case that we've seen, and basically everybody is susceptible. Possibly I could make S of 0 n-1, but it doesn't make any difference in the long run. All right, so essentially what we've got is we've got a differential equation, a set of differential equations, which is basically an engine of change. Right? Differential equations tell you how things move and change. So that's why they're great for modeling biology, because biology is always changing. And like every engine, you need a starting key, and the starting key is our initial conditions. All right, so we're basically going to start it and then see what happens. All right, so using the next generation method, and the reason the next generation method is a good one is because if you're finding R naught, this only focuses in on the infectious classes. So it reduces the dimension of the problem. And that means we can find our R naught using our F and V matrices. So F is essentially a matrix of new infections, and V is the negative, the transfer terms out of every other compartment. So we can find our FV inverse and find our reproduction number. And our reproduction number consists of two pieces. There's contributions from symptomatic individuals and contributions from asymptomatic individuals. Right? And actually, it happily splits up nicely into this 1 minus P and P parts. And of course, there's the eta there and the alpha, which are, these are factors associated with asymptomatic individuals. Either how much, faster you recover is alpha, or how much sort of less transmission you have. That's the eta. All right, so great. Now, let's just think about this for a moment. We know R naught, right? R naught is easily measured by counting, right? You effectively can count how many secondary infections are you getting, right? So R naught was well known. We also know N, obviously. We knew the fraction who were asymptomatic, so we knew our P. What we didn't know was, well, we knew the recovery or death rate as well, but we didn't know the differences between the asymptomatic and symptomatic individuals. And we also don't know the transmission rate. Right, that's actually a very hard one to measure because it's sort of the nonlinear parameter. I mean, it itself is just a constant, but it's associated with nonlinear things in the model. Okay, so let's use R naught to kind of determine some likely beta values, right? Given that we don't yet necessarily know the asymptomatic factors as well, right? So if I basically sub in what I do know and rearrange, then I can write beta in this form here. So it depends on alpha and eta. Right, and I don't know alpha and eta, or at least I didn't at the time. So we can experiment with these and see what if they are, extreme values, right? What if asymptomatic people are identical to symptomatic people, or what if, as was actually thought at the time, asymptomatic people had no role to play? There was some serious talk about that. They said, oh, it doesn't matter if you're asymptomatic, you can't even pass on the virus. That is not true, we know now, but of course that's an extreme case. So we could look at basically the ends and the middle as well, right? So I'm going to look at what if asymptomatic people are identical to symptomatic people? So eta and alpha are the same. And in that case, I would backtrack to find beta. In this case is 2.7 times 10 to the minus 6. What if asymptomatic people didn't infect? We know that's wrong, but it's a boundary case. So in this case, beta would have to be much higher, right? Why is beta higher here? It's because that means the symptomatic individuals are doing much more infecting, actually, if there weren't any contribution from the asymptomatic individuals. So that means actually it would actually be a more infectious disease if that's the case. Or we could try somewhere in the middle, right? So what if they are 50% as transmissible, but recover twice as fast? So this was just basically a sort of compromise case to try and figure out a median beta. I'm actually going to focus on the first two because they give us upper and lower bounds, but I'll look at the third one as well as a kind of likely case. But of course, we could play with this and we can update it with more information, which I will also put in later. Okay. Oh, by the way, here's a picture of Ottawa in the winter. This is exactly what it looks like now. I live not far from the canal. The canal is the longest skating rink in the world. No, it's the largest skating rink. I think there's a slightly longer one that's thinner. So I think they say it's the largest skating rink in the world. It's I think 7 kilometers long. It's about 5 miles. And it's lovely. And they never advertise it because they're absolutely terrified of students being put off by the winter, even though I think it's glorious and beautiful if you're not actually in it, but it's a little colder when you are. All right, so we wanted to run several possible long-term outcomes. What if we did nothing, which was an option at the time, or what if we cut contact rates, say, by 50%? Right, so people were just encountering other individuals less. Now, of course, we know that that's far more than that happened because everyone started to stay home. But at the time, this was not on the books necessarily. So what if we reduce contacts? All right, so that's our sort of major intervention here. All right, well, we have to look at the different cases. So what if transmission is high and we do no interventions, right? So in this case, the red is the symptomatic individuals. So when the first case appears, it's basically down the bottom there, almost at day 0. And then we have the dead individuals. So I'll just use the mouse here. There it is. So the first case appears down the bottom here, and then the dead individuals occur about 115 days later. The first dead individual would appear. So that's kind of our worst case scenario if we did nothing. Right? So it might be some time before anyone died on campus because it's a pretty healthy population, of course. But nevertheless, that's what we would be talking about. Right? And if we kind of run the time series, then you can see this kind of has a very classic epidemic curve. So for those familiar with diseases, you see this kind of like, infection wave happens. Right, and so we might see something like this where it was happening over the course of about a year with the symptomatic individuals. There was lower numbers for the asymptomatic individuals, right? And if we look in the inset, then you can see, well, your peak would be about 6,000 people, and you would eventually have about 63 dead individuals on campus. And of course, most people get infected, so susceptibles really reduce, but of course, the vast majority recover. So this disease would kind of sweep through campus, killing 63 people, infecting 6,000 at its peak. And well, I guess it's not really up to me to decide, is that acceptable or not? This is what I can pass on to the policymakers, so the upper administration, and just say, well, here's the worst case scenario. But what if we look at some other scenarios? All right, so if the transmission is low, right, then you can see that the first death on campus for lower transmission would occur later, because lower transmission means there's more time to circulate and so on. So that would occur at about day 150. And this was the best case scenario of that intervention. And in this case, you can see that there are not as many dead people. There's only 58 instead of 63, but there are more infections. But that's because with lower transmission, it kind of means that you kind of have to spread it more to kind of do the same damage, because the R naught is still the same, remember. All right. So in this case, not as many people get infected, right? So it's a better scenario. There's not as many dead people. It takes a little bit longer for the first death to appear, but of course, this is not a great option. We don't really want 58 dead students on campus, right? And remember, we're assuming here that everybody is low risk, right? And so the actual numbers could be higher if we started taking the high risk people into account. All right. So what if? Well, so this is just to summarize. If we didn't intervene, right, then the worst case scenario would result in the first death 115 days after the first symptomatic individual is diagnosed, leading to 63 deaths. The best case scenario has the first death 150 days after diagnosis, so the first case, eventually leading to 58 deaths. And I would say, you know, this doesn't look good. And certainly at the time, this did not look great. I mean, now I'd say we live with a lot more deaths from COVID all over, but I think deaths among students was not something that we really want. And so what if we halve the contacts? Right. And if we halve the contacts, so this is the worst case scenario with the high transmission, but we now reduce the contact rate by 50%, then you could see that, well, after the first symptomatic case appears on campus, it's about 450 days till the first death. And so we've basically delayed what's happening. And how bad is it? It's not as bad. It's, in fact, a lot less bad. We only have 25 dead. And at the peak, you only have 700 infected. So that's a significant improvement over the 6,000 from the no contact reduction case. And a lot of people don't get infected in the first place, right? So susceptibles are still pretty high. Right. Now, is 25 deaths too many? That's, again, a very complicated argument, but it's certainly better than 63. And that was in the worst case scenario. In the best case scenario, well, now we've significantly delayed it, right? So if the best case scenario with 50% reduction says, well, the first death is not happening for like 1,800 days. And how bad is it? It's not that bad, right? Now, I still have 5 deaths on campus, but look at this, I would have like 25 cases at most. You know, very few people get infected in the first place. Most people recover. This is pretty good, right? Again, not perfect, but, you know, not too bad. All right, so let me just sum up. For high transmission, if we cut contacts in half, the first death occurs 450 days after diagnosis, right? Much later than 115. We get 25 instead of 63 deaths. For low transmission, the first death occurs 1850 days after the first diagnosis, so much later than 150, eventually leading to 5 deaths, which is a lot better than 58. So what we see is that reduction of contacts can really make a big difference here. Now, there is a caveat I need to put in, which is, remember that we said there was no replacement of susceptibles and there was no death from other reasons, or actually no leaving for other reasons. If you're talking about 1850 days, that's many years. We would probably have some people perhaps dying for other reasons, but also just leaving campus because they graduate, right? So I would say this is an idealized scenario that if I was actually going to look at this in more detail, right, then I would start putting in the replacement of susceptibles, right? So I would have, you know, everybody can leave, but new susceptibles would arrive, possibly new infected individuals can arrive and so on. So I would put in the vital dynamics if I wanted to do this in more detail. So this was really just to illustrate, you know, some of the outcomes, because I'm not really predicting that exactly 1850 days after first diagnosis, there'll be the first death. What I'm saying is it's less bad if you can cut contacts. All right, so, well, I gave that to the upper administration about 2 in the morning, actually. And then the next morning, I say one day, it was like a few hours, basically as soon as they got it, they shut everything. Right? They were like, you have made an excellent point. We're shutting the whole thing down. And this was a little bit earlier than most campuses closed. And eventually, well, pretty quickly, actually, things closed. But we were one of the first out of the gate, and we were like, shut everything down. Basically, contact reduction is very clearly going to make a difference. And it's still closed today, like it's except for essential research. So some labs and so on, we have not opened up anything. So even though some schools opened up, some high schools and so on, and other campuses have been talking about different things, we've been very strong on like, no, we are not opening until it is safe to do so. And I think that's really the right call, to be honest. Now, of course, some things have to be done. So labs that can't be left unattended. summer 2020, fall 2020, winter 2021. Actually, I just found out 2 days ago that summer 2021 is also going to be online. I suspect the fall will be as well, unless vaccination rates really take off. But I don't think that's going to happen by then. So yeah, it's basically we're shut down until this is over. All right. So I just want to talk a bit more about some further information that came to light since March 12th. So that was basically knowing what we knew at the time. What can we do? But of course, we don't have the option of like running scenarios for many days with 50% contacts because there's nobody on campus. Well, not nobody, but there's very few. So there've been no deaths on campus, but actually there was a case, right? So on July 17th, the member of support staff tested positive. And so this was discovered on July 20th. So if you like, the clock is ticking, but of course the contact rate has been reduced massively. It's not just 50%, it's probably like 90 something percent. So will there be a death on campus? Well, it's a very different scenario, right? We are not mingling the way we were, that the number of people on campus has massively dropped. So we could run future scenarios for sure and see, but I think at some point the model has served its purpose, because the model was about, what should we do on March 12th? And we would probably make a new model if we wanted to do something about like, well, let's think about reopening. All right, so, well, I'll talk about that a little too. All right, so I just mentioned the Ottawa pandemic. So Ottawa pandemic has followed the typical age distribution for COVID-19. So that means there were significant infections in hospitals, retirement homes, long-term care facilities, but very few in the community. So Ottawa is like well, they say it's a mid-sized city for Canada. That means probably for you guys, it's a small city. It feels like a small town that has a lot of things in it because it happens to be the capital, but so it's got its share of like museums and art galleries and so on, but it doesn't have that many people in the scheme of things. All right, so here's public health data. This was August 15th, and what we see for this, let's turn the mouse on. Basically things that they were going up, but they basically plateaued. Like the number of deaths had effectively plateaued at about 264 by then. You see these sort of waves happening. So the green here is in communities. So the community outbreak had sort of started but went down. So there's not much in the community. The sporadic ones, that was basically sort of people bringing it in from outside. We kind of had this kind of early wave that then we shut down, and then there was some summer outbreaks happening where people were coming in from other cities once they started opening stuff up, and then of course bring some cases, but they were dealt with pretty well. But the big spikes here, this is institutions. This was nursing homes and retirement homes and so on. So of course they were quite bad, and then eventually went down. And the age distribution is kind of what you would expect here. The gender makeup, more women get infected than men, largely because more women work in service industries and hospitality and so on. So they become more susceptible. So the first wave basically ended in July. There were 2,000 cases and about 260 deaths out of a population of 1.4 million people. Well, that's in the greater Ottawa area. Sporadic cases peaked in mid to late March at 27 cases per day. And then there was a much larger outbreak in long-term care facilities, which peaked at 93 cases per day on April 25th. All right, so let me talk about possibilities for reopening. All right, so what if we reopened campus with appropriate caution? Right, so obviously we'll be wearing masks. There'll be partial remote learning. They've talked about having small classes in big classrooms. So if you have a class of 20 people, but you're in a 200-person classroom, they can spread out. All right, so there's some options that have been discussed. So the idea is that contacts with symptomatic people would be significantly lower, because if you have any symptoms, you do not come to campus. Right, so that would offset their higher rate of viral shedding compared to asymptomatic individuals. So most of the transmission then would presumably be driven by asymptomatic people, right? Because they don't know they're sick, so they're still coming to campus. And one tweak that was actually pointed out later was we'd matched the death rate to younger individuals. But of course, campus might consist primarily of asymptomatic people, so we could match the rate to that as well. So younger people are less infected by the disease, right? So what if the death rate is proportional to the symptomatic rate, right? So basically, like the ratio between the population death rate and the population symptomatic rate, we could say, well, let's try and match that to the campus death rate versus the campus symptomatic rate. And so what we found was basically revised proportions and revised transmission rates in the case where we had The asymptomatic people recovered twice as fast, but were half as infectious. So this is kind of the median case. You notice here the beta is much higher because to sustain the same naught, you'd have to have a lot more spreading, so a lot more infection really sort of happening behind the scenes here. All right, so if that's the case, this is kind of our, what if we reopen campus case, right? Then we could see like, well, we might look something like this, where again, we're seeing, oops, sorry. We're seeing that, what, 300 cases at the peak and 2 deaths. If 2 deaths is acceptable, maybe that's okay. But this is the kind of situation where, people are becoming infected. As you can see that most people do become infected, the susceptibles go very low. So this is our worst case scenario when there are very few symptomatic individuals, right? So we peak at 300 instead of 6,000, okay, that's cool. First death is predicted at a similar time. So that was 127 days after diagnosis instead of 115. Total deaths is kept at 2. That's a significant improvement on 63 or whatever. And the other cases produced similar results. It wasn't wildly different. All right, so obviously we're not suggesting lockdown remain in place for 13 years. This is not a long-term kind of prognosis here. It's really up to political leaders to decide if 2 or 25 or 63 deaths on campus is acceptable. And of course, these are all ballpark estimates that are subject to lots of stochastic variations and so on that we did not include. The lockdown contact reduction in practice was, of course, much greater than 50% among students, although it's probably quite heterogeneous. So students may be essential workers, so a lot of them work at grocery stores and things like that, so they may be much more exposed perhaps than people even just a few years older than them. If you're an office worker and you're just working from home, that's quite different to if you're a student who's holding down 3 part-time jobs and moving between them. So there's some other issues that we did not include that we might want to think about if we were revising this. Some of the limitations here, this was a snapshot in time. Right, so this was March 12th. The data that we had was limited. The model doesn't include our vital dynamics, so our birth and death rates. There was therefore no influx of new susceptibles. There was no leaving rate of students. So the former is probably true, but the latter is probably not. Right, so university policies, of course, change. I say may change. They did change as a result of lockdown. There are fewer international students. Certainly, my master's student from South Korea, like she basically went home as soon as she could, and so she gets up at 4 in the morning to do her tutorials. And I was like, well, that's she's like, I want to spend time with my grandmother while she's still around. And I was like, fair enough, that's quite reasonable. And of course, the increase in distance learning via Zoom and other things. All right, so all my classes are certainly online, and I I'm teaching calculus for 200 people, and I don't know what their faces look like, but we talk a lot in the chat. All right, so some of the limitations for the modeling, we assumed mass action transmission. So this assumes that individuals are well mixed, right? That assumption may not hold in lockdown, it probably won't, because the number of contacts is reduced, and so is the strength of their interactions. Recovered individuals were assumed to be immune to reinfection. We know that's not true entirely. Certainly some people can be infected more than once, for sure, whereas, well, some people, of course, are, as far as we know, not getting reinfected, but we only have a year's worth of data on this disease. Some of the benefits, though, of this model, let's turn that off, were its rapid development. So this was done very quickly, about 12 hours. Its flexibility in considering multiple cases where data was lacking, and its ability to directly answer questions posed by the university administration. Right? So basically, the speed was really helpful, I think. So what we've seen is, here's an example of a role that models can play during a fast-moving pandemic. You can see the power to make predictions and their ability to inform policy when linked to decision-making processes. So of course, I think a lot of us who develop models, would love our models to make their way into policy, but generally speaking, it doesn't work like that. It doesn't, policymakers aren't just reading academic papers and looking for ideas. I would say where I have had my work make its way into policy is always where I have basically embedded the modeling in the process from the very beginning, and it's about people, right? If you can make relationships with people who are the movers and the shakers, then they're more likely to listen to you. They don't generally say like, oh yeah, you have a good result, I'll just use it. Like, they have to be part of the process. All right, so let me just sum up the first part. These results illustrate the interface between theoretical mathematics, numerical simulations, real-world data, and human behavior. Right? And I think all of these things are important, right? And we try and do the best that we can. There are, of course, many limitations, but we can also get some insights, I think, pretty quickly. So modeling a disease during the very early stages of a pandemic, we could assess multiple scenarios quickly, and I would say cheaply, right? So the great thing about math is it's very cheap. You can just run some scenarios. Of course, you have to run multiple scenarios to account for limitations in what you may not know, because you only have so much information that you know at the time, but you can do it, right? I don't have to run clinical trials and spend months and so on like figuring stuff out. I can do it very fast, right? So I'd like to sort of question, how valid is this, right? So I've got some scenarios, but of course my scenarios didn't play out because things massively changed because of lockdown, right? So decisions are made, right? I'd say armed with useful predictions, but the question is more generally, are these doing the right thing or not, right? Are these working? We make these predictions and stuff changes, so it's hard to test whether the predictions came true or not. But that's not always true. Okay, so let me talk about in part 2, basically how reliable are models, right? So it's as I said, models have the advantage of being fast and cheap, right? So that's great, you can certainly employ them. And in the early stages of any pandemic, models are often employed very quickly because they're kind of the frontier of what's happening. But they're often based on a meager, meager data and limited biological understanding, right? So often the people making the models are not biologists, right? We sort of have some, relationship with the biology, but we're not, as informed about the biology perhaps as we could be. And the data that exists is only what exists, right? And you may have some data and you may have very little data sometimes, and yet you still need to kind of come up with answers. So what I'm going to look at is not for COVID-19, but the past couple of pandemics, basically the past 3 respiratory pandemics over the last sort of 15, 20 years. How good were the early models that happened then at predicting what happened in the end? All right, so I'm going to look at SARS, MERS, and swine flu. These are very similar pandemics. SARS and MERS are both coronaviruses, and swine flu is also a respiratory disease. And these were differing levels of, worldwide pandemics. And what I'd like to see, though, is how effective were the studies that were published at the time in predicting the outcome, right? So, often a new disease comes up and, people get together and say, oh yeah, I should model this and I'll come up with an early model and then see what happens. Let's go back and check and see how well they did, right? And from this, can we figure out which factors made predictions more accurate, right? Were there any glaring failures, right? Where did the models fail in their predictions? All right, so let's talk about SARS first. So the original SARS, it spread from Guangdong province in China to many of the world's largest cities. 17 countries were infected. There were 8,500 cases and 774 deaths. At the time, I remember very clearly at the time, this was a major pandemic, right? We kind of may laugh at these numbers now because they seem so tiny compared to what we have with COVID-19, but this was serious stuff, right? And I was living near Toronto at the time, and Toronto was a city that was majorly affected. Lots of things were being shut down and so on. So there was a lot of fear and a lot of, tension around this. And the data that we had was basically limited to what was reported to hospitals and health authorities. So there wasn't a huge amount of data available. Data did not include asymptomatic cases or anyone who didn't seek treatment and therefore was not seen by the system. So we only have limited understanding. So I'm going to just go through some of the key papers that were published at the time. So Riley et al., they looked at the first 1,500 cases from Hong Kong, and they determined that R0 was probably between about 2.7 and 3.7. They used a stochastic metapopulation compartment model, which accounted for high variability in transmission. So SARS had a lot of variability happening, much more than COVID actually, because they had super spreaders. So there were some people who were much more infectious than others, like significantly so. Like a few people were kind of these like typhoid Marys wandering around infecting massive numbers of people, and most people were not infecting very many. All right. There's also changes caused by chance versus interventions. They had a SEIHRD, so susceptible, exposed, infected, which is also infectious, hospitalized, recovered, and dead. Right, and the latent and infectious compartments were divided into multiple categories, and they concluded that SARS had low to moderate transmissibility. So Chow et al., they used a cumulative number of SARS cases from 2 weeks in the beginning of the epidemic in Ontario, Hong Kong, and Singapore. So 3 of the major spots. They estimated that R0 was a bit lower. They said about 1.1 to 1.2, and various points of uncertainty, such as how infectious were asymptomatic individuals, and were there differing levels of susceptibility in the susceptible population. Also, did the diagnosis rate alter the risk? So, are people changing their behavior based on either their own diagnoses or other people's? And they concluded that up to 10% of the world could be infected. Now, of course, we know that did not happen, but I guess, the question is, could that have happened without interventions? So maybe. And we certainly see from a different coronavirus, way more than 10% of the world got infected. Lipsitch et al., they analyzed the first 205 cases from Singapore using a stochastic transmission model. They estimated R0 to be between 2.2 and 3.6. And the high variability here was attributed to the uncertainty in the distribution of secondary infections and the serial interval distribution. They concluded that SSEs are super spreading events. So at the time they actually talked about super spreading people, but it's better to say super spreading events, I think. But super spreading events can have a drastic effect on the number of secondary cases if present at the beginning of an outbreak. They have less effect later on, but if you basically have a super spreader and they happen to be one of the early people infected, they can do a lot of damage. Choi and Pak used Canadian data up to April 6, 2003, and a simple exponential model to estimate R0 as 1.5. They concluded that up to 50,000 total cases would occur by June 25th without interventions. Right, but of course there were interventions. Zhou and Yan, sorry, I think it's Chao and Yan, used a Richards curve to fit early infection data from Singapore, Hong Kong, and Beijing. They estimated that R0 was 2.7 in Singapore, 2.1 in Hong Kong, and 3.8 in Beijing. And they also predicted the maximum number of cases over the epidemic. They said it would be 748 in Hong Kong, 207 in Singapore, and 2,500 in Beijing. Let me just compare that with the actual numbers. The actual numbers were 1,755, 238, and more than 5,000. So wow, they got Hong Kong and Singapore pretty much on the money there. That's very impressive. The Beijing numbers were not as good. And their conclusion at the time was that the higher R0 in Beijing was due to a delay in exercising effective control measures. And so I think that that's probably what explains the much higher ultimate numbers as well. That basically, if you can't mobilize quickly enough, then epidemic is going to spiral out of control, which is basically what we saw in kind of January, February last year. We didn't mobilize at all, and now epidemic spiraled. All right, so this highlighted a difficulty faced by all research in 2003, which was that the transmission mechanism of the virus was not known at the time. And furthermore, you couldn't necessarily assume that there was going to be timely and appropriate intervention on the part of health officials. And that was sadly the case in Beijing at the time. Now, of course, a lot of Asian countries learned significant lessons from SARS, and that's why they were much more prepared for COVID-19. Because they basically they paid the price for not mobilizing quickly enough, and therefore when COVID-19 came along, people were able to lock down, wear masks, and so on much more quickly than we were. We were just not good at that, and getting people to wear masks took time, and that's valuable time at the beginning that could have saved a lot of lives. All right, so let's compare to how it actually went. Right, so SARS was mostly done by 2003. By the end of 2003, there were a couple of cases in 2004, but it was basically over by then. And retrospective studies said that R0 was somewhere between 2 and 4, depending on the method used. And so 3 of these papers, Riley, Lipsitch, and Shao and Yan, had their estimates directly in the post-disease range, and others had their estimates slightly outside. So I'd say, on the whole, not too bad. And especially those particularly the numbers in Hong Kong and Singapore was fantastic. So one of the factors that sort of came up here was properly estimating government response is a crucial factor in modeling an outbreak. China's government and healthcare structure likely played a role in allowing SARS to go beyond 3,000 to 4,000 cases. That was what was estimated by Zhao and Yan. And estimates that were based on Toronto or Singapore's healthcare systems were probably optimistic for a society of China's capabilities at the time. And if you remember when COVID-19 first came in China, they were massively building hospitals. They built, 10,000 person hospitals and stuff like that in a weekend and stuff. So, China's capabilities are a lot better now than they were. All right. So this highlights the unpredictability of agents at the macro level versus the individual level. All right, some other limitations are the public's response to news of the virus. So people are unpredictable. And also the magnitude of isolation once the epidemic is underway. This is hard to predict. And we've seen that, of course, on a larger scale with COVID-19. The capacity of hospitals is not always straightforward. There are issues with beds and ventilators and staff and so on that kind of have to be taken into account. So there are lots of other places to explore. But for early ballpark numbers, they did pretty well. All right, so MERS, that's kind of the camel disease. So it's a respiratory disease similar to SARS and COVID-19. Started in bats, just like the others, but mainly transmitted by camels. It has recurrent outbreaks in the Arabian Peninsula since 2012. And there's low transmissibility for the most part, but you get these sometimes kind of like rapid outbreaks, usually originating in hospital settings. So you kind of have these huge blow-ups sometimes. So Kachamez and colleagues used data up to August 2013. So they used 111 cases, averaging across all detected clusters, using cases from Saudi Arabia, Jordan, and the United Arab Emirates. These clusters consisted of non-resident travelers and non-hospital originating cases. They estimated that R0 was less than 1, about 0.63, and the doubling time was about 90 days. And so they concluded that these inhomogeneous mixing patterns led to a reduced rate of infection. Right. So for the most part, this disease should not take off, but then of course you have these sudden rapid outbreaks happening. Ifan et al. Used a sequential Bayesian method to assess Saudi Arabia's experience with different clusters over a 2-year period. They divided the country into 5 geographical clusters: north, south, east, west, and center. Right. They estimated R0 was between 0.85 and 0.97 in all 5 regions, but the sensitivity analysis showed that central and western regions could get as high as 1.08 or 1.12. So their conclusion was that contact frequency, hospital procedures, and population density really matter. These things are probably driving when you get these outbreaks. Brevin et al. They only used 64 cases. They used the first 55 to develop their model, and they validated it with the next 9 cases. This was vastly fewer than most studies. Their estimated R0 was 0.69. And I would say this lower value was basically due to optimism about contact tracing and isolation procedures during outbreaks. So they said that people will probably be pretty good at doing this. Their conclusion was that MERS did not have pandemic potential, but enhanced surveillance and vigorous searches for the original animal hosts were still important. Okay, well, how did they do on MERS? The R0 for MERS, not counting the super spreading events, was 0.47. This is in line with Kachamez and Brevin, who predicted sort of 0.6 or so. The Brevin one is particularly impressive given how few cases they built their model on. And in the case of highly transmissible events that happen rapidly, R0 is between 1 and 7 initially, and then it tapers off. So you get these very large outbreaks with high R0, but then it reduces quickly. All right, so both SARS and MERS had these super spreading events with very high R0s briefly. And Chow et al. Also used 4 nosocomial outbreaks of SARS and MERS, outbreaks in hospitals, to show the effect of super spreading events. And in each case, hospitals were disproportionately large carriers of both diseases. It was actually, you couldn't really access hospitals once the disease went out unless it was very dire. And so part of the problem is, of course, healthcare workers have to rotate, family members visit patients, at least until they were not allowed to. And this is one of those lessons we learned pretty well for COVID-19. They shut down a lot of hospital visitations pretty quick, right? That was a lesson that was learned from SARS in the Western world. All right, so the last one I want to talk about is swine flu. So swine flu, so it was also known as H1N1, but of course there are many H1N1s, including the 1918 influenza pandemic. So the media called it swine flu because it likely jumped from influenza in pigs. This ran from April 2009 to August 2010, and seasonal flu vaccines offered almost no cross protection. 80% of swine flu deaths were people under 65, which is quite different to both seasonal influenza and also what we see in SARS and COVID-19, that it primarily killed younger people. Robertson Nishiura used a renewal process to model the first 2 months of cases in New Zealand in a group of students returning from Mexico. So they considered imported cases alongside local growth, accounting for infection age distribution. They estimated that R0 was about 1.25 with a fairly tight confidence interval. And they concluded that stochasticity in the early stages of diseases was important. Fraser et al. Looked at they tried to estimate the total number of people in Mexico using back calculation methods, estimating R0 to be about 1.5. And they used 3 different epidemiological methods to find this. They used generation time distributions of other seasonal viruses, Bayesian coalescent population analysis, and time series of reported disease onsets. And they concluded that age specificity played a key role in accurately fitting the model to data. Nishiura et al. Used Japanese data to determine age-specific estimates, looking at 361 cases. 287 of them were teenagers, so 80% of them were teenagers. They estimated that R0 was about 2, and they concluded that the high R0 value here was likely due to high contact rates among teenagers. Well, that's something we see sometimes too with teenagers partying in pandemics. And they concluded that minors could sustain swine flu transmission amongst themselves. All right, so subsequent R0 estimates basically said, well, it was probably about between 1.3 and 1.7, with some northern countries having values above 2. So Fraser et al. Were right in this range, and others were pretty close. So early studies did a good job of mapping the trajectory of the virus in its initial stage. And this held true when the epidemic passed in one continuous wave, but the same is not true for multiple waves. So this is where the modeling did not work, right? Some waves had similar R0s, like some subsequent waves, but others had quite a bit larger R0s. So pandemics often come in waves, as we've seen in COVID-19, and the second and third waves can be much stronger, as we've both seen and probably are about to see very soon. The second swine flu wave was more than 4 times worse than the first in Canada. Hospital admissions were almost 5 times as high, ICU admissions 4 times as high, deaths were 4.6 times as high. And estimates can be derived for the spreading capability of the first wave using specific data. But what they did not do is they were not able to predict either how potent the second wave was or how likely it was to occur, because not everywhere got a second wave in swine flu, right? So, it's very hard to say when will the second wave occur, or even if it will occur. And if it does occur, how bad is it going to be? These are very hard things to predict from the first waves, right? So many countries experienced more than one wave, so the US, UK, Mexico, and Canada, but several experienced only one, especially in the Southern Hemisphere. So contributing factors include the weather, population densities, social pandemic procedures, and healthcare systems. Determining factors that would predict a single versus multiple waves would be really handy if we could do that. So in summary, mathematical modeling has the potential to make surprisingly accurate predictions in the early stages of an epidemic, even despite the paucity of data. Right, so things I did in one day are things that Brevin et al. Did with a very few number of cases. Can basically, you could make predictions for sure, and some of these predictions we see are surprisingly good. The methodologies that basically had the most success generally included stochastic effects. So this is one thing that really came out of this kind of survey was, yeah, the stochastic stuff really helps. Right, so these models placed greater focus on quantifying the effect of super spreading events, but spatial considerations also helped, especially if you had highly populated dense regions like Hong Kong. So basically very, very big cities, the spatial stuff was another factor that really mattered. The place where it didn't work so well was waves. So that models did very well in predicting the spread of a single wave, but they were not so good at predicting for later waves. Subsequent waves can lead to high transmissibility, worse symptoms, and increased mortality rates, which we saw in Canada and the UK for swine flu, and I think we've seen in COVID-19. So there's still work to be done, still lessons to be learned, but I think we've got a good overview here. The last thing I just want to mention is some other general models, right? So models that made general predictions for kind of respiratory illnesses that weren't linked to specific diseases. And there's, of course, many such models, and they're not always based on strict biological accuracy. But I just want to mention a few of these because some of them have made quite insightful forecasts. So Wu and Cowling looked at the state of models predicting influenza pandemics, and they suggested that travel restrictions would have little effect in stopping the pandemic. I think we see that play out pretty well 10 years later. The most effective mitigation would be combinations of antiviral treatment and prophylaxis, as well as non-pharmaceutical inventions such as quarantine, isolation, school closure, and social distancing. Well, that could be right from COVID. This is a decade earlier, and all the things they're saying were basically exactly what we needed to do, as we learned. Morse et al. Looked at the emergence of novel infectious diseases from zoonoses. So zoonoses are animal-derived diseases. They account for more than 60% of emerging infectious diseases that have been identified since 1940. So most diseases jump species from animals to us. It's important to note that no one has ever predicted a new pathogen before its first appearance. So that's another weakness that we have. But once an outbreak is underway, then predictions are pretty, well, they're doable and actually often quite accurate. So there are basically 3 pandemic stages. There's no human infection, there's localized human infection, and then widespread human transmission with global dissemination. And I think we all know where we are in this current one. All right, so Hubert and Catriel, they suggested the next pandemic would cause severe mortality, morbidity, and extensive economic impact. Well, check, check, and check. Modern medicine would provide advantages. Yes, it does, but these are offset by the ability of transportation networks to rapidly propagate a disease around the globe. Again, check. Saunders-Hastings et al., and actually full disclosure, I'm one of them, We examined strategies for mitigating a potential influenza pandemic. Using hospital resource capacity as a limiting factor. This was done in 2017. We consider both pharmaceutical interventions, such as vaccines and antivirals, but also non-pharmaceutical interventions, such as school closures, community contact reduction, hand hygiene, mask use, voluntary isolation, and quarantine. And I have to say, I'd kind of forgotten about this until I'd gone back and looked at it. I was like, oh yeah, right. This is all could be COVID stuff, right? All of these things came to pass during COVID-19 just 2 years later, or 3 years later. All right. So what we can see from this is modeling can make good general predictions. Right, so we can derive meaningful estimates for disease spread, for the maximum number of infections, an approximate fadeaway date using appropriate model selection and characteristics. The ability of early COVID-19 models to predict the disease course is possible, at least for single waves. I think one of the biggest differences between COVID and the other ones are the scale, right? This is the largest disease we've seen for more than 100 years. So that's a big factor. But otherwise, it's pretty straightforward, actually. It falls right into the sort of region of like typical respiratory disease. All right, so just to sum up, if we can understand how a pandemic might unfold during its early stages, this would be great, right? So current and future pandemics can be modeled with some degree of accuracy, at least in the first wave. Subsequent waves should therefore be treated as distinct waves. Kind of, if you just restart again in the second wave, we'll get a sense of how that's going to go. And pandemic models are most useful when they include stochasticity, spatial considerations, and super spreading events. So models can be a powerful tool for prediction when they're harnessed correctly. So I'm just going to put up 2 references here. I'd also like to acknowledge my student, Christian Kostas-Vass, and my colleague, Alyssa Schwartz, for the stuff about the past pandemics. Work on the modeling on the campus was published at a conference, well, it was presented at a conference and then published in their proceedings last year. And then the other one is published in Mathematical Biosciences and Engineering. If anyone wants to read these or anything else, my website is fully accessible. The QR code there takes you straight to the same link. And I will stop there and say thank you very much.